Day 22, part 2. We're back. Example B, same sort of thing. We got one of these letter ones, and we have to find a single vector that represents this, and there's some fiddling to do. We can either do it uh, geometrically, like using the picture, or using the letters, and I'm going to do both. You only have to do one. The only thing is, if you do it by pictures and make a mistake, it's really hard to see where your mistake was. So anyway, NQ is there. MQ is there. So we want to subtract these two vectors. I want to subtract these two vectors. Well, first of all, we don't want to think of this as subtracting. We would like to think of this as add. So I'm immediately going to change this to QM, right? And then add. So I'm going to think of this way right away. Why subtract vectors? And now I sort of got to get these together, so it's either a parallelogram rule or a triangle rule. So notice, I suppose I could move this one, couldn't I? There. If I wanted to do that, I could. Right? Because this vector and this vector were equal. We said that's a property of a rhombus. And then where's the answer? Where's the answer? It's right here. Start at the tail, end at the tip, triangle rule. It's XM is the answer. Right? Okay, well, what's a way to do that using letters? Oh, okay. Well, what did we do? We already did that part, QM, and then we said, well, NX is actually the same thing as XQ. And that's kind of a nice way to do this is we knew if this was going to get together, these two have to be the same, the tip to tail. And there's the XM, just like we knew. Okay, a couple of examples. These are application ones, and as we'll see, pretty much any time we have an application one that's adding, we could be finding it. We could be doing a subtract question if we think about it just a little bit differently. Here we go. This is a straightforward one, but it'll set us up. Ferd is capable of paddling his paddle boat in still water at 1.4 meters per second. Ferd is paddling directly against the current. So the idea is this is Ferd paddling away 1.4 meters, and we're pretending the river, this is the river here, and he's paddling up the river, and the current is dragging him back directly against the current. We don't know this how much the current is. Ferdette, who's sitting over here watching, sees Ferd go by at 0.6. So it's kind of like it gives us the answer, right? Usually we think of these boat questions as how much you're paddling in the boat plus the current gives you the overall velocity vector, right? And it did here, right? This is the 0.6 meters that Ferdette sees. That's kind of like the answer. Ferd's paddling plus the current is giving me the velocity, but I really won't want to find the current, right? Well, how do I do that? It's not too hard to see because they're kind of in the same direction. The current is just 0.8 meters per second opposite to Ferd, right? Opposite Ferd. Or we could say that it's negative 0.8 meters per second. And if I just stuck to the algebra, watch this. If I want to solve for C, then that's going to be V minus B. The velocity that we see 0.6, subtract Ferd paddling at 1.4 is negative 0.8 meters per second, and that's all good. And this idea of adding and subtracting vectors in situations like this is kind of the reason why we're doing this entire unit. So the next one's a good one. A plane needs to travel at 250 kilometers an hour with a bearing of 130 degrees to reach its destination on time. All right, so the idea is we've got a little, oops, that's good enough. I'm not going to do it to scale this time. Um, the plane is traveling at a bearing of 130 degrees. So where's that? 130 degrees, that would be 0, 90, there's 130 there, I'm going to pretend, where that's 40 degrees, right? An extra 40. Write that in there. Maybe in red. Do all my angles in red, why not? That's 40, right? Because that bearing is 130. There is a wind from 80 kilometers per hour southwest. So this idea of a wind being from somewhere, and sometimes they say the wind is pushing the plane this direction, but from kind of implies, from down here somewhere, from down here in the southwest, it's pushing on the plane, right? All the time. Pushing on the plane, pushing on the plane, pushing on the plane, pushing on the plane. We often will draw it up here. So from the southwest is down here, means it's actually pushing the plane northeast, which is a little bit confusing, but you got to watch the language. When a wind is from somewhere, it's pushing it the opposite direction. So here my wind is 80, and this has got to be 250. So this has got to be the answer. I'm going to make that one red, just because, or no, not red, because my angles were red. I'm going to make it blue, because then that's my answer. Make that blue too, just because. That's my answer. Because what I need to figure out what direction the plane should head at, so that the wind puts it back onto this course. So if this is like Toronto and this is Boston or something like that, if he flies straight there, the wind's going to push him into the Atlantic Ocean. That would be bad. So he sort of plans to go off track, and the wind pushes him back on track, right? Well, how far? Well, kind of, if this is the answer, the vector I want to find is this vector right here, right? And I'm going to actually make a copy of this wind vector, so we can see where it came from, so we can see some angles, right? Because if this is from the southwest, what's this angle in here? Well, this is 45 and this is 45, isn't it? And this is the vector that I want to find. I'm going to make it dotted, maybe just, or you can make it a different color, whatever you want. So that's, we're going to steer this way. The wind's going to push us back to be on track, which is the blue one. Well, how do we do this? Well, that's 80. That means this is 80. And you see we've got a bunch of angles here. We don't know what this angle is because we don't know the direction to head. We'll actually have to find that. What else do we know? Inside this triangle, do I know this angle? No, don't know that angle. But this angle, do I know that angle? Remember, all vectors are parallel. Parallel lines here. Parallel lines here. And we could think of this as still heading at that south, from southwest to northeast, 45 degrees. I could set up, but that's 85 in there, isn't it? That angle is Z pattern with these two angles. That's 85 right there. And so if I want to find the airspeed, which I'll call this one here, this is the airspeed, the speed that the plane has to set. Now this is the same as the one we did last class, which is a cosine law to find the magnitude. Old hat for us now, right? I think the hardest thing in these vector questions I'm leaving out a bunch of steps here because you're good at the cosine law. Hardest thing is finding that angle. That's 85 from all this information is somewhat surprising. And if you draw a good diagram first, then you're not going to make an error. It doesn't have to be to scale this time, but draw a good diagram. Now, that means the airspeed should be 255. So notice that even though to be on time, he's supposed to travel at 250, he's got to set, or she's got to set, the pilot's got to set the plane to go up 255 kilometers per hour. Otherwise, they won't be on time because the wind's sort of working against them a little bit. What's the bearing? Well, I'm going to use this, find that angle here, because then the bearing will be that angle, 90 plus 40 plus whatever that little angle is, and I'm going to use the sine law. Just as I'm working here, a word about the sine law. For some reason, the book doesn't like the sine law, and I know why. It's got to do with the ambiguous case. It's got to do with, being careful about drawing your diagrams and all that sort of thing. Cross multiply and divide. And you end up ... after a bit. I think I got 18 degrees for there. Hopefully you got something that's similar. 18 degrees. And then the bearing is 90 plus 40 plus my 18 degrees. The bearing is 108, 158. Is that right? 148. 148. So then the pilot should steer 255 kilometers per hour with a bearing of 148. And notice that if you did it this way, you could say south so many degrees east, and that would work out just fine as well. Okay, I think that's it. It sure is. Okay, subtracting vectors. Say two.